let's talk about microscope. So in year 6 in junior science, you have learned how to use microscope. If any of you study biology, then again you will be very familiar with microscope. And apparently microscope is for us to see things are very tiny. And today the microscope that we are talking about in this video is referring to optical microscope. Okay, so there are actually another kind of microscope called the electron microscope, which the mechanism is totally different. So today we just focus on the optical telescope. So let's take a quick look on the name of different part, and hopefully that helps you to recall how you used the microscope earlier. In fact, the names here are not necessary to recall in the physics exam, but I think it's more like a way so that we can communicate easily. The most important part in microscope for physics is actually eyepiece and of course the objective lens, and in fact both of these are convex lens. Okay, both of these are convex lens. And the other thing that may relate to physics also is of course a light from the bottom. So there is a light here, and where you can adjust the aperture, which in biology they call it diaphragm, which is same as a camera, like the inlet of the camera. You can adjust the size of the aperture. So in that case, control the light, whether it's too bright or too dim. And the other important thing for you to use in microscope, you may recall, is there are two focus knob. It's a little similar to if you went to the astrophysics camp, overnight camp. The telescope also have two focus knob, which one of them is giving you a big change. We call it coarse focus, and the other one is called the fine focus. So you usually will change the coarse focus first, and then for a rough change, and then you do the fine change. And if you recall how you use it, you'll find out when you change for different objective lens. Apparently there are 3 different power of objective lens, and one of them can magnify the most, and the others may magnify less. For each of them, they would have different focus you have to adjust, and that is something to do apparently with the light diagram. Okay, so we'll talk about that later. One thing that you may want to pay attention and realize is that when we adjust the focus, we are actually adjusting the distance between the objective lens to the stage. So we are adjusting this up or down, but you should realize that actually for the eyepiece to the lens, that means here, alright, this tube, you may find out that it's always the same, because you never change the eyepiece, of course. And that actually also means no matter which objective lens you use, this distance is always fixed, is always a constant. Okay, so that is actually explainable by the physics you learned today. First of all, I would actually want you to think about, if you are the engineer of, or just simply a designer, you may say, designing the microscope. If I tell you that you have 2 convex lenses, how would you like to put them together and get them work as a microscope? Try to spend maybe a minute thinking about like how you may want to put. Apparently is, of course, is simply 2 convex lenses put in the same line, but how would you like to locate them so that they work as a microscope? You may want to pause the video and we'll explain later. Okay, so here is a example of the microscope light diagram, which I obtained from the textbook. You can find it from the textbook. We will learn how to draw later on. There will be an example or exercise in this video at the end. You will try to draw it again, but for now I think it may be easier for you to simply take a look of how is it drawn first. Okay, so actually one thing that I would like you to do before I explain, earlier just now I asked you how do you like to design. Let's take a look. I mean, before I answer that question, let's take a look of the ray diagram first. And for now, once again, I will want you to pause the video and try to take a look of this diagram. And I want you to do one thing, that is to find a mistake. Okay, very common in this textbook. But I think in a way you would be able to maybe understand a little bit more and take it as a challenge. Okay, what I mean is by the mistake is that there is one of the ray here is wrong. Okay, but then it doesn't affect the outcome. I mean, at the end of the day, you still find the image forming here. This is the final image. So pause the video, think about it, and get back to us. Okay, so let's take a look and try to follow me here. First of all, what we have is we have the object here, which is extremely tiny over here. I hope you can see it. Let me try to zoom in a bit more. Okay, extremely tiny here. So, and of course that is common because when you are using microscope, you are more like looking at some very tiny stuff. So that's why it will be very small. And you can see the magnification by looking at the result is much bigger, and that is why we use it for looking at things like cells or even bacteria. So the first line you would like to draw is actually the green line here, like usual, like these two green lines, which the first one actually go horizontally and then go through F, okay, and then the next one is simply go through the optical center. Okay, so for these two, you will find the intersection, which actually I don't think this is a really nice diagram because I actually think the intersection is here. Instead, I don't know why they didn't draw it properly. But then, never mind. Okay, let's pretend it is here. Well, they intersect here. We can actually adjust the focus. I think if we can adjust the focus to be more like further up, I think like around here, then it might be better. Okay, but let's just assume it's formed here. Okay, so we get the green one and then the intermediate one, which we can label it H prime for intermediate image. And what you could do afterwards is how that will go through the second lens, which is the eyepiece. And of course, as usual, the first light you would like to draw is a light that go from the tip of the image going through to the center of the lens, and then you need another line to find the intersection as usual. So what you could do is you will want to find a horizontal line. I mean, the light of course in radiate out in all directions, so you would like to choose the one that is going parallel to the principal axis and then going through the focal focus here. And you will find that they are diverging, and that's very normal, and you will find they will be able to project backward and form an virtual image here, and then that's how you see the final image here. So the answer for like the mistake is actually here. Okay, so here this line is wrong because obviously you can see that it did not change at the lens. So I think it's a tiny mistake, I would say, and it's just something that you need to I mean, you could find it out, okay, if you want. So I think that's why the line actually, if you draw it properly, then it should be more like, I think it's be more like this, and that is why the intersection should actually be here instead. But and actually, never mind. Okay, so I think the main idea is like what I said, the green one and then these two one, and then you trace it back. Okay, it's actually very simple. So back to the question about, so how do we actually manipulate the two convex lens and make it as a microscope? I think the first thing that you may want to record is the relationship between the object and image for a simple convex lens. So let's take a look again. So here's a simulation that you may use. I'll put the link in the description, and I think all of you should know it already. Basically what you can do is you can take a look of here. This is convex lens already, converging lens, and if the image is near the lens, between lens to f, then what you have is the image will form at the back of the object, and it will be magnified until you're approaching f. It will become larger and larger and larger. At infinity, it's kind of like the tipping point of the image. It will go from the back infinity to the other end, which is here. And again, if you look at the similar triangle, you know that the image around maybe like somewhere here will be much magnified, and then once you move away from f, it will get smaller, and now it's the same size and smaller and smaller and smaller. Okay, so how is this related to microscope? And the reason is for the two, if you look at the diagram again, what you actually we actually try to manipulate the convex lens is by putting the objective lens, I should say, and also the eyepiece in a way so that both of these lenses are magnifying the image as much as possible. That means if you look at the object, it plays very near, just a little bit exceeding the focus of the first lens, the objective lens. That means in our case will be something like here. Okay, of course you don't want to get exactly at f, because that would not be able to form any clear image. It will be buried, but then a little bit more, that it will be a very large image in that case. At the same time, then you may ask, hey, then why don't we do this? The reason why we don't do this is because when you do this, the image already formed at the back of the image. Then you cannot use another lens to further magnify. So that's why we do this one first. Okay, so you get a magnified image. I know it's inverted, but it doesn't matter. Okay, doesn't matter it's inverted, but then it is real. This is very important. This is real image. So then that's how you get the intermediate image here, and then that real image can be used, since it's on the right hand side, it can be used for another lens, which is eyepiece. So imagine you already got this intermediate image which acts as an object for the second lens. Then you can really use, now what you can see here is this intermediate image is adjusted so that it is a little bit closer to the lens from the focus point. So right next to the focus point, but a little bit closer to the lens. So that's in our case would be around, not here, but a little bit here. Okay, so then in that case you can get basically the best magnification in that case twice. At the same time, yes, you will form a virtual image, but that's fine. You can with our eye we can still see the virtual image like that. Okay, so this is how people design the microscope, and it has been still using nowadays for optical microscope. Isn't that amazing? If you think about it, we try to manipulate the best out of the best from the convex lens. If you are still feeling confused with how to draw the diagram, I will recommend you to watch this video. I will put the link in the description, and it will guide you through step by step. It's a very similar diagram that like how I show you just now. Okay, so take a look if you want. If you're okay with the diagram, then right now I want you to take a look of your textbook on page 20 to page 21. Okay, and what I want you to look into is basically the proof, and of course it would be nice if you try to read the paragraph also, but ultimately what I want you to do is I want you to find out and understand how we prove this equation and also this equation. Okay, and then see if you can find this equation in the data booklet also. Okay, pause the video and do it now. Okay, let's go through it together. So first of all, what we do is we try to prove this equation, right? So first of all, we have to understand what it is. The thing that we are trying to prove is the angular magnification of the whole microscope overall. Okay, so what how we define angular magnification is, if you watch the previous video, then you should know that it is the big M equals to the aided one over the unaided one. Okay, so unaided means as if you try to look at the object directly under the distance, and usually is we call the near point 25 cm. So that's why theta is h, which is original object size, divided by the d, which is the distance from the object. Again, is usually 25 cm if we are talking about near point. So the idea why is equal, again, if you recall, is because of the tangent theta. When the angle is small, it will be similar to theta. And as in for our case here, our aided one, as we are talking about the overall and angular magnification, then we are referring to the final image. So that's why it's h prime prime. If you refer to the diagram, that is basically this one. Okay, so h prime prime is actually this one. Okay, h prime prime, and then you have the distance of v2. Okay, and then that is tangent theta you can find, which equal to theta. You could also actually use u2 and also h prime, but then I think this one it depends on situation, see which one is more convenient, but usually I think h prime prime will be more useful if you want to calculate the final image size. So that's why I think here we use this one. So by simply substituting these two things into the definition, back to definition, and you have this, and simply you rearrange them, and you would be able to do a magic trick in mathematics, that is using h prime divide h prime, which is 1, so you can always do that. And the best part of doing this is you will find out the first one here, h prime divide h prime prime divide h prime is actually the objective lens magnification, and also h prime over h is the eyepiece magnification. Okay, or is it? Or actually it's opposite, I should say. But anyway, I think you get the idea. One of them is, this, and one of them is the other one. Here, be careful. The small m is the linear magnification. Okay, linear magnification, and always use a big M for angular magnification. And for the later part here, this is just simply direct copying to this d over v2. Okay, so this is a general equation. Be careful about this. Okay, so later on there's another equation here, right? But then here you may want to note it down on your textbook that to remind yourself this is general equation. In fact, if you try to look at the data booklet, you will find out there is no equation about this on the data booklet. The one that I have here, you have here under C.2, we are now in C.2. This is for telescope, which we will talk about that in the next subchapter of video. But there is no microscope here, and so what do you do then, right? So this is an equation that I would say you would need to use 100%. You need to use whenever you see microscope. So I would recommend you to simply copy this on your data booklet, the one that you've been using always, and by the time when you take the IB exam, you take a look of the whole data booklet, and there must be some one or two. For example, if you recall in chapter 12, the de Broglie equation about the matter wave, that equation is not on your data booklet. So that is an equation you have to put down on your data booklet, and maybe before the day before the exam, you may want to just quickly remind yourself about that. And same for this equation. Okay, once again, this is a general equation. That means no matter where you want to form the image, that is the equation. Okay, D is where the image is, and that is flexible. Okay, so let's move on to the next one. We have the next page saying that since we have, if we have the normal adjustment, that means the image is at the near point, again 25 cm, then you can change just now that general equation into this form of equation. So be careful, this is a special case. You may want to put it down. Special case as in when you are having the near point. And once again, I want to reiterate to you as a big picture that when you learn physics, you need to figure out and be very clear about the equation, whether they are the general case or a special case. I'll give you another example. Newton's second law, okay, you always know F equals to ma, and this is a general equation. There are times where when you talk about free falling, and in that case F equals to the weight mg equals to ma, assuming there is no air resistance, then that would equal, and then you will get m will cancel, and then you will get g equals to a, and this is only a special case, okay, which you cannot always assume it is true. But for F equals ma, nearly, except of course we know relativity, that would basically break the equation. But then for most of the content in IB, then G equals to A is actually a special case. You can actually never take it for granted. Same for our case here, back to this situation, that this equation is a special case. That means you cannot abuse it anytime for microscope. It's only true and when it's only convenient to you when it is this special case, when the image is forming at the near point. The way to prove it is very simple. If you look at this equation again, when you are at near point, then V2, which is again the image distance for the final image, is at near point. So like I said, your eye here, and then this is 25 cm. And then in that case, from this equation, this fraction d over will become d over d. So that means it will be exactly the same. Okay, and so the equation before evolving to this form, you may want to say before that it will be angular magnification equal to MO times ME, both linear, this one. Okay, and this ME, because it's the eyepiece, alright, the one that you are looking at, then you can refer to our previous video, which we talk about for a single lens. If they are forming the image at near point, then you can replace the linear magnification with this one, which is on the data booklet also. Is it on the data booklet? Oh yes, this is on data booklet. Alright, so the one that we talk about in the previous video. Okay, and one interesting thing that you may find out and also written in the textbook here is that in this case, again, when it is at near point, then the angular and linear magnification would be the same. Alright, for actually not of the eyepiece, I should say of the angular magnification would be the same in that case. Okay, so like I said, no formula here is provided, so you need to know how to work it out. Alright, so here is a very interesting way to interpret, or useful way to interpret that, and let me try to rephrase the situation so that you can get even better. So here, let me give you a very realistic hypothetical question that I would like to ask you to fit to our current situation nowadays. I think all of you know there are different kinds of masks, surgical masks nowadays, and there were different tests. I just grabbed this picture from Google. So there are different category, I should say, or classified as different category. So things like BFE, VFE, and PFE, and B refer to bacteria, V refer to virus. I think P is referring to particle. So the coronavirus apparently is virus. So the size is around that much. The question I want to ask you is, what would be the expected angular magnification required if we want to observe, as like say biologists, observe these coronavirus from 2 micrometer, so that we can see by eye, so let's say 1 cm, in terms of the image, final image, at the near point, forming at near point. What would that angular magnification require it would be? So try to pause the video, work it out, and get back to us. Okay, so the calculation is actually quite simple. What you have to do is you may recall the fundamental definition of angular magnification, and by that means for each of them, and that would be how we do, similar to how we derived the equation earlier for this one, and simply substituting everything inside the h prime prime, which is the one that you wish to see, and the actual size of the virus, and assuming that we are having the normal adjustment, so the d will cancel each other. At the end, you will be able to obtain, actually it's not 500, it should be 5,000. Yeah, 330. Yeah, so 5,000 will be the magnification that is required. So that will be extremely difficult. And in fact, by using the optical microscope, if you try to Google it, you'll find out. If you're interested to try to find out, I will put the link in the description. I think here, it was hard to see, as you can see. I mean, of course, it's 2011. It was hard to see, but then using some other technique will enable us to see the virus using the optical microscope. The reason why we can't actually see it is not because of angular magnification is not high enough. You may say, hey, 5,000 seems quite large. If you try to search, 5,000 is actually achievable. However, it's something to do with the resolving power instead. So just like this picture, if you try to zoom in too much, and the resolving power will be, or the things are too small, the quality of the structure will be very hard to see, like the one here. So it is quite marginal, and it's hard to observe very clearly. And there is an equation where you can rely on to find out whether the image can be resolved by using this equation. And in fact, you have already learned this equation in previous chapter. I think in the wave chapter 11, chapter 10, no, not chapter 11, you have learned about the resolving power, and that is an equation similar to what we use. So you can use this equation. And you may wonder, so how come that is 0.61? And that's something to do actually with times 2. Actually, I prefer the equation on coordinate much more, because that is the original equation, rather than simplify it. So you may want to take a look of this equation, and for using it, it's very simple. You just substitute everything inside, and it's a refractive index. Okay, so even though the textbook said you do not need to know this formula for the exam, but I just double check with the official syllabus about microscope, that of course, like we did, construct the diagram, interpret the diagram at normal adjustment, solving problem with angular magnification. Here it said you need to solve the problem regarding the resolution of the microscope as well. So I don't really think it is true that you don't need to know the formula. I think it's safer, once again, that you put down this formula in your data booklet also, in case you are asked about this. But in terms of using it, I think it's quite straightforward. They may just tell you the wavelength at the end, the angle, or a certain way to work out the angle, and you can find the resolving power or the distance here. Okay, so in the next video we try to do more exercise